These are the spiders in your yard.
Hello YouTube. This is a video I've been looking forward to making ever since I began this channel. Because even though this spider isn't rare or even unusual, it is easily one of my favorite species to observe and work with. Because these are just so beautiful and so remarkable. They're large enough to get noticed, and they love to make great big webs in inconvenient places, kind of like when your toddler takes the crayons to the living room wall when you're not looking. You might be able to see the beauty in the artwork, but you would have preferred it to be done somewhere else. A lot of people notice them, and a lot of people want to know what they are. I see them come up all the time on spider identification groups. Meet Araneus diadematus, the Cross Orbweaver, also known as the European garden spider, the Diadem Spider, and probably a couple of other names as well. Now, if you happen to live where this particular species doesn't occur, that's okay, because its close relatives occur pretty much all over the planet, and a lot of what I'll say here will hold true for them as well. I'll get into the mysteries of their elaborate webs and how they use them, what these spiders eat, how they reproduce, their intelligence, and the future ahead of them. And I'm going to tell you about the sensory ability these spiders have that you never would have guessed, the astonishing way it actually works, and why you might want to be careful what you say around them. There are things about these spiders you never even thought to wonder about that are absolutely incredible. There's a lot to discuss, so get comfy and we'll get into it. One of the really nice things about orb weavers is that they sort of announce themselves as what they are, with their web. Very different from sheet webs, cobwebs, or funnel webs, these webs, called orb webs, are made up of a central hub with spokes radiating from the center and a spiral of thread expanding from that hub. The moment you see a spider at home in one of these orb webs, you've instantly narrowed the spider down to just a handful of families, a group called the Orbweaver Guild. Now, Orbweaver identification can be kind of tricky, but this particular species of Orbweaver has a dead giveaway. If we look at the abdomen, or opistosoma, of this spider, it's pretty hard to miss this. This is why this species is referred to as the Cross Orbweaver. It helps that these spiders can get fairly large, with the females reaching 20 millimeters, or about 3/4 of an inch, in body length. So it's usually fairly easy to see this mark. Now the markings surrounding this cross pattern can vary a lot, and the coloration of the abdomen can also range from nearly black to a light tan. But this cross will always be there, not just something kind of like it, but this actual cross. Let's look at some of the other features of this spider though. You can see there are sort of these shoulders to the abdomen, giving it an almost triangular sort of shape, as opposed to a more rounded shape like this Mangora species. Spiders in the Araneus genus all have this general abdomen shape, and are called angulate and round-shouldered orb weavers. A little further back on the abdomen, towards the sides, you've got this cool foliate pattern that zigzags back and forth along either side, tapering to the end. And you can see the legs are banded and quite spiny, which is pretty typical of orb weavers in general. The eye arrangement is kind of cool, with this sort of trapezoid in the middle and a close pair out to each side, which is typical of the Araneidae family these spiders belong to. Now, sometimes, because of where they've woven their web, you can only see the underside of them, what's known as a ventral view. From this angle, you'll see a dark stripe down the middle of the abdomen, with these two shapes that kind of look like brackets on the sides that sort of curve in right here. And if you forget for a moment what you're looking at and just sort of visualize these two parts as big eyes, we end up with a very angry octopus. See? Now that you've seen this, you can't unsee it. It's all you're going to see when you see orb weavers from the underside now. A number of close relatives of this spider have this angry octopus thing going on, so it's not as diagnostic as the cross, but a spider with this marking is going to be in the same family. Now, all of these things do hold true for both the males and the females. The primary difference is that the males will look a lot smaller and thinner. Their abdomens look tiny in proportion to those of females, and mature males will, as usual, have enlarged palps. but the markings will generally be the same. There are a few species that look quite a bit like the Cross Orbweaver, but if you make a mistake and misidentify a spider like this one for Araneus diadematus, it's really not the end of the world. These are all in the Araneidae family, they're all pretty similar, and behave mostly the same way, and nobody will call the spider identification police. Side note, Charlotte from E.B. White's Charlotte's Web was an Araneus cavaticus, also known as the barn orbweaver, the same genus as our Cross Orbweaver here, just a different actual species. And orbweavers like these occur virtually everywhere in the world,
except Antarctica.
We say that a lot in biology, don't we?
Yeah, I hear it's cold
We
there.
sure do.
This one species isn't quite worldwide, so many of you may not have encountered it, just its relatives. If we look at the iNaturalist data, we can see that in North America, it seems limited to this strip along the west coast and this area on the east coast and around the Great Lakes. The data from GBIF, the Global Biodiversity Information Facility, seems to corroborate this. So the whole central part of the continent seems to not have this species of orbweaver. However, they're found virtually everywhere in Western Europe, and seem to venture a bit east from there. That's unsurprising, since these spiders are native to Europe. The species itself was described by Swedish arachnologist Carl Alexander Cleric in 1757, in his groundbreaking book Svenska spindlar, or Swedish spiders. And together with our friend the zebra jumping spider, Salticus senecis, Araneus diadematus was one of the first creatures ever to be given a Latin binomial name. So it's been known in Europe for well over 250 years, and Europeans can find this species both on their front porch and deep into the forest. But in the regions they populate in North America, researchers have noticed an interesting trend. North American cross orbweavers are never far from human structures. They're outside, in our backyards and hedges and stuff, but most of the time when we go into the forests of the US and Canada, they disappear. This is probably related to the fact that they're an introduced species in North America. The first record I could find of them in the US was in November of 1895, and in Canada the earliest was in 1919 in Quebec. Now, where would you expect to find these in terms of actual terrain features? You won't usually find these crawling on the ground like a wolf spider, or climbing around on walls like a jumping spider. You'll find them in a web. And for that, they need at least a bit of a vertical element, because that web needs to be attached to something. Sometimes that's a tree branch, sometimes it's a fence or your car's radio antenna. Sometimes it's your doorway, and you have to ruin the spider's hard work just to get out of your own house. Or you could explain to your boss why you won't be into work that day. Sounds like as good a reason as any to me. And once they've built a web somewhere, they're likely to stay there, taking the web down and rebuilding it every night. In 1996, Samuel Shaka did a study examining the early stages of web construction with the Cross Orbweaver. Part of that study was measuring the distance the spiders walked while exploring a new site to spin a web. Based on that alone, it became clear that in terms of energy expenditure and material cost, it was much, much cheaper for the spider to stay in one place. When they take the web down, they leave the frame and anchor threads in place, so they're reusing parts of it already. And they eat what they take down, allowing them to reclaim the proteins and nutrients in the silk and recycle them. They can also tweak and optimize the web in the rebuilding, based on how it has worked so far. So unless they've got a terribly compelling reason not to, they'll stay at the same address forever. In arachnology, this is called site fidelity, how strongly a spider insists on staying in one place and making that its home. And it's this site fidelity that has allowed me to keep one of these spiders in only semi-captivity for months. This is Claire. She hitched a ride inside with a piece of patio furniture last fall and was just a little spiderling at the time. She was like this big. Around the same time, I was experimenting with keeping orbweavers in captivity, so I thought I'd give it a shot with her. There were some inconveniences along the way, and if you're interested, I tell that story on my Patreon page, along with some other behind-the-scenes stuff, But ultimately, and half by accident, I convinced her to weave a web in this little setup. And she's been there for months now. I can pick this up and move it, and her whole web just comes with it. I put her in the kitchen when we get flies. But I keep feeding her, so as far as she's concerned, this spot between these two damaged, retired arrows is just fine. There's no enclosure, there are no walls or glass. She could come down and wander off anytime she liked, but she doesn't. This is site fidelity. So Claire is now my office Orbweaver. We usually find these spiders outdoors though, making them a largish spider that finds our porches, doorways, and backyards the perfect place to make their homes. Meaning that for many people, the obvious next question is... It's ironic that at Halloween, the image of the orb web is used to instill fear. Because while nearly all spiders have venom, no spiders that make this kind of web are known to be medically significant. Now those of you with trust issues are wondering, what do you mean by medically significant?
What do you mean? What do you mean? What do you mean?
An animal is only considered medically significant if its venom can cause death, serious injury, or a condition that would require the immediate help of a doctor. That doesn't mean that the venom has no effect at all. The few records of bites we have from these spiders caused redness, sometimes some itching and swelling, and some pain, much like a mosquito bite. But sometimes a bit of nausea, headache, or muscle cramps were reported. That's a bit more than a mosquito bite, but that was it. In fact, a 2016 study found that the venom of these spiders seemed designed to selectively target insects and had no effect on vertebrates. So, probably unpleasant, but nothing to review your will over, and symptoms resolved within a couple of weeks, usually less than that. Interestingly, the only spiders we know of that don't have venom at all, the Uluboridae family, make orb webs. So, if anything, this shape, this form of web architecture, is an immediate indicator that the spider who lives there is not dangerous. And by the way, since everyone is talking about it at the time I'm making this video, this applies to the Joro spider as well. It's also a kind of orb weaver, and nobody needs to panic about it. They're not aggressive at all either. If one of these ends up on you, it has no interest in biting you. As far as the spider is concerned, you're just a big moving mass that it's walking on, that probably feels kind of gross, because they virtually never walk on skin in nature. It's only going to bite if it feels threatened, like if it's being pinched or squeezed against your skin. And that's unlikely, because they don't hide in shoes or clothes or gloves like a brown recluse might. So these are not a spider you need to worry about from a medical perspective. Even if you manage to get bitten, which you would basically have to be trying to do, you'd be fine. So what do these spiders enjoy biting? Well, if you're not a spider person, this part might make you appreciate these animals a little more. Due to the nature of the orb webs, suspended in midair as they are, these spiders tend to prey almost entirely on flying insects. Most often flies and mosquitoes, with some wasps and the like thrown in there. Even bees or butterflies on occasion. They're what's called a generalist predator, so they don't have just one specific prey specialization. They'll eat nearly anything that gets caught in their web. What surprised me, though, was that they're not quite strict carnivores. Orb webs filter a lot of stuff out of the air, not just insects. A 2013 study by Benjamin Eggs and Dirk Sanders did what's called a stable isotope analysis to determine what some juvenile cross orb weavers in Bern, Switzerland had been eating. By sampling the area to see what resources the spiders there had available, then testing their actual tissues, they were able to estimate what the spiders were eating. Turns out, about 10 to 40% of the diet of these little spiderlings was pollen. And the spiders weren't eating it by accident when they took down and ate their own webs at the end of the day. The pollen particles were too big for the spiders to be ingesting accidentally. They were actually covering the pollen grains with their digestive juices just like they would with prey, to dissolve the outer coating, then sucking up the dissolved nutrients. So they were definitely eating it on purpose when they could have just cut it out of the web. This tells us that pollen is actually an important source of nutrients for these spiders, at least at this life stage. When it comes to flying insects, again, a lot of their diet is smaller flies and mosquitoes and the like. They'll also prey on some tougher insects, like, for instance, Harmonia axyridis, the Asian lady beetle, which is considered to be one of the most invasive insects in the world. These were introduced in North America and Europe as a pest control agent, and, well, they got out of hand and started affecting native species. What's interesting is the Asian lady beetle possesses a chemical defense not found in European species of lady beetles, and yet the European Araneus diadematus seems to have no trouble killing and digesting these things. Of course, this brings us to the question of how these spiders are catching these things in the first place, and this is where things get really interesting. The construction of these ore webs from start to finish is such an elaborate process that I made it its own video, and you can check that out here. And I'll link it in the description as well. But the TLDR version of how they do this goes something like this. The spider gets as high as possible, vertically, not chemically, though the latter has been done, and lets out a line of silk. It drifts until it snags on something, then the spider uses that to drop down and make a Y shape. This becomes the first sort of scaffold, from which the spider adds some frame threads, which form the border of the web, and radials, which are the spokes of the web. Now all of that is made of non-sticky thread. Then it makes an auxiliary spiral, which starts in the middle and is pretty wide, which stabilizes the whole thing during construction. And then it makes the actual capture spiral, which is made of silk coated in droplets of glue, working from the outside in, and using the auxiliary spiral as a guide. Now, the capture spiral doesn't go all the way to the center. The spider leaves a free zone that it can duck through to move from one side of the web to the other, and it puts a non-sticky spiral at the hub that it can sort of sit on. If that sounds complicated, keep in mind that this is the Coles Notes version of the process. Check out episode 3 of the Spider Basics series for the full explanation, and also a discussion of drug use among spiders. What is even wilder, though, is how the web works, and how these spiders can use it. Most people would figure out pretty quickly that an orb weaver's web functions like a net to catch flying insects, and this is somewhat straightforward. But it turns out there is way more to these webs than we might realize at first glance. The capture spiral is made of a very elastic kind of silk, which can be stretched to several times its length without breaking, and which is coated in little droplets of glue that a flying insect would get stuck to, and the web, being very thin, is nearly invisible to insects, and also humans until we walk face first into one. But there's a lot of math that goes into the actual design. Spider silk is made mostly of proteins, so it's actually metabolically expensive for the spider to produce, and it can only produce so much. Meaning, the spider needs to make the web as efficient an insect catching device as it can. And that involves two main geometrical concepts: mesh width and capture area. Once the frame and radii are built, the capture spiral will have a given total length. If the spider places the spirals close together, it will catch smaller prey, but have less area. If the spider places them further apart, it'll miss smaller prey, but have a greater area. Larger prey might require more than one capture thread to restrain them. However, bumping into one thread might interrupt flight enough to make an insect tumble into contact with more sticky threads. The spider makes decisions about mesh width based on what prey is around, among other factors. One study fed orb weavers fruit flies for a while, but when they switched to mosquitoes, the spiders immediately made more widely spaced capture spirals, and went back to the tight spirals when the researchers switched back to the smaller prey. Also, the hub isn't in the actual center of the web. It's a little above center. And there are three things to note about that bottom portion. 1, it's bigger. 2, the mesh is a little tighter. And 3, the glue droplets there are bigger. Turns out there's a reason for this. In a 1994 study, Aluna Brizdiart and Fritz Vollrath timed how long it took these spiders to reach prey in the 4 quadrants of the web, which they deemed north, south, east, and west. And they found that the spiders could move to the south, or more or less downwards, the fastest, nearly twice as fast as they could move upwards, meaning they could cover more distance in the same amount of time when rushing to grab prey in the southern quadrant of the web. To figure out whether this was due to the web geometry or due to gravity, they had some spiders make webs, then turned the webs horizontally and introduced prey. When horizontal, the spiders didn't run faster toward the south anymore. And when they turned the webs upside down, the spiders again could move just as fast downwards, which was now the north end of the web, as before. These spiders invest more in the southern portion of the web. It's really their best prospect, because to actually catch prey, they've got to get to it before it can break free. And gravity helps them cover more area in this direction, so they make more web in that direction. So what happens when we play a trick on these spiders and mess with gravity? Well, if we wanted to make gravity stronger, we could put the spiders in a great big centrifuge, I guess, but that would be crazy. Wait, nope. Fritz Vollrath and Tamara Kohler actually did this in 1996, apparently, and found that up to 3.5 Gs, there wasn't much change, but at 15 Gs, the geometry was quite different. They called their paper Mechanics of Silk Produced by Loaded Spiders. Anyway, but what about when gravity is removed altogether? It took a few tries to get this one right, apparently. A couple of Cross Orbweavers were sent to space in 1973, but the photos weren't really good enough to learn much. Researchers tried again in 2008, but the fruit flies that were provided for the spiders took over the enclosure and obscured the glass completely. But in 2011, the opportunity arose once more, and 2 Trichonephila clavipes, golden silk orbweavers, rocketed into space to hang out on the International Space Station. This time they sort of got it right, and could see what they got up to, and Samuel Shaka, Stephanie Countryman, and Paula Cushing wrote a paper about it in 2020. The species was chosen specifically because they tend to make highly asymmetrical webs, with the hub quite a bit above center. The webs made in space were much more symmetrical, as there wasn't really an up or down. However, they weren't completely symmetrical. The hub was often positioned a bit off-center, closest to the light source of the enclosure. And researchers also noticed that while this species, like our Cross Orbweaver, normally hangs at the hub of the web facing down, the ones in space faced no particular direction when the lights were off. But when the lights were on, they faced away from the light. So gravity seems to be the primary indicator of direction for orbweavers, but in the absence of gravity, they're probably using the light from the sky to orient themselves, which is probably about as much as their eyes are good for. Whether in space or on Earth, though, these webs with their super elastic capture spiral and sticky glue do the job very well. Abriziart and Vollrath captured footage of a bumblebee, which is not a small insect, in full flight becoming trapped in the web as a result of contact with a single strand. The single strand caused the bee to tumble, then coming into contact with other sticky strands, which collectively had the adhesive strength to restrain it long enough for the spider to come make the kill. But it's not enough for the web to simply catch the prey. The spider has to know somehow that the prey has been caught. And like virtually all orbweavers, this spider has terrible vision and is effectively blind. The web is actually an extension of the spider's senses. When an insect gets stuck in the web, it usually struggles to get free, making the strands of the web vibrate. Unsurprisingly, the spider can feel those vibrations, but what is surprising is how much those vibrations tell them. A 2019 paper by Mortimer, Soler, Wilkins, and Vollrath took a look at this. They identified 3 different kinds of vibrations within webs: lateral, transversal, and longitudinal. Using computer modeling, they investigated how vibrations from prey would travel through the web, and how the different kinds of vibrations would arrive at each of the spider's 8 legs when sitting at the hub, like these spiders do. By measuring amplitudes, time differences, and ratios between the 3 different vibrations, they identified consistent patterns that changed based on where in the web a vibration began, and they found that those patterns provide enough information to tell the spider not just what direction the prey is in, but how far from the hub it is as well, pinpointing its exact location in the web. It's not actually known whether the spiders are capable of detecting these patterns, but the fact that the patterns are there makes me suspect that they can. In nature, information is seldom wasted, and we know that spiders build every part of these webs very deliberately, right down to tensioning the lines to specific parameters. The anchor threads, for instance, are under about 10 times the tension of the radial threads, and the spider can make minor adjustments to this at will. No part of this web is an accident, so my own personal suspicion is that if the web can provide this kind of information, it's probably because the spider makes it so. The caveat is that this information is only available to the spider from the hub of the web, and often the spider's hiding at the edge instead of hanging in the center. When they do this, if you look closely, you'll see a single strand of silk running from the hub to wherever the spider is hiding, and you'll see that the spider has one leg out on that line. This is sort of like watching your fishing pole for twitches in the line. If prey gets caught in the web, the spider will know it, but it won't have the locational information. Watch what happens when I put prey into the web somewhat between Claire and the hub. She runs to the hub, not the prey. There, she quickly obtains that locational information, then rushes to the prey. But from the hub, the spider knows exactly what's happening in that web. The functions of the web don't end there, though. I mentioned a surprising sensory ability that these spiders have. Well, if you ever wondered if these spiders are hanging out in their webs watching you while you try to relax on your deck, they're not. Like I said, they're practically blind. They may, however, be listening to you. In animals, hearing ability is often restricted by the physical size of the organism's body. You need an auditory organ of a certain size to be able to gather enough auditory information to be of any real use. And given that these spiders are so small, you wouldn't think that they'd be able to hear much. Effectively, that's true, if all we're talking about is the spider's body. But a 2022 study led by Jian Zhu and Junpeng Lai at Binghamton University in New York found that spiders may be overcoming this limitation by outsourcing the job of hearing to, you guessed it, their web. The team found that an orb web functions as a hyperacute acoustic antenna, essentially a giant external eardrum. Except it actually has better efficiency and responsivity than all previously known eardrums in animals. The team collected some orb weavers, in this case Lerinioides sclopitarius, a species common across much of the US and closely related to our Araneus diadematus here, and had them spin their webs in wooden frames. Then sang them some songs and checked to see if the spiders bopped along. I mean, not really, but sort of. They placed the spiders and their webs into an anechoic room, a space where sound doesn't reflect and bounce around, and emitted tones from a speaker 3 meters away, about 10 feet, straight onto the web, and also from half a meter away, about 1.5 feet, at 45-degree angles to the web. And they videotaped the spiders' reactions, experimenting with different volumes and different tones. They found that at 68 decibels and 3 meters away, about half the spiders responded to a 200 Hz tone, about this A flat note. And at 88 decibels, about the volume of a running blender, 11 out of 12 of them did. Responses included crouching, stretching, raising the forelegs, and turning. And what's even cooler is that the spiders could tell which direction the sound was coming from. When they responded by turning, they turned toward the source of the sound. Reviewing the frequencies and sounds made by many predators and prey of these spiders, the team was able to determine that these spiders should be able to detect those predators and prey at distances of over 10 meters, or 33 feet. And they can accurately localize those sounds as well. Using their 8 legs, they can also tune the web in real time by changing the tensions on the various strands, allowing the web to filter out unimportant signals or amplify more important ones. By using their webs, they increase their sensory surface area up to 10,000 times that of the spiders themselves, providing them a wealth of information they would not otherwise have. This is one of the coolest things I learned in researching these spiders. A question we've probably heard since elementary school is, how do spiders not get stuck in their own webs? Turns out scientists have been working on that one for a really long time, and there were a few theories around, but here's what we know now. If we look closely at this image, we can see that these threads, which are the radii, are just plain silk, while these threads, which are part of the capture spiral, are covered in these little tiny droplets of glue. That's why they're sticky. Most of the time, these spiders are staying on the non-sticky parts of the web, and they actually grasp the strand. They do this by using a middle hook on the ends of their feet. This smooth hook presses the thread against these serrated bristles, and that acts like a clamp that can easily be applied or released. But this isn't always the case. They use their rear legs to pull the sticky silk out of their spinnerets when they make the capture spiral, and somehow don't get stuck to that. So what's going on here? A 2012 study out of Costa Rica by R.D. Briceño and W.G. Eberhard suggests that orb weavers have 3 features that allow them to not get stuck: special setae, special techniques, and a non-stick coating. Briceño and Eberhard examined 2 species of orb weaver, Nepheloclavipes and Gasteracantha cancroformis. A lot of Latin names sound like magic spells, but that one more than most.
Gasteracantha cancroformis!
This is a very cool looking spider, but it does in fact belong to the same family as our Cross Orbweaver here, so we can expect it to be pretty similar. To figure this all out, first they filmed the spiders actually making the webs to see what happened when their legs touched the sticky silk. It seemed to not really stick at all, which was curious. Unfortunately, to figure out the rest, they had to euthanize some spiders and remove their legs. They also took samples of the sticky capture spiral silk. Then they pushed the leg onto the threads in the same way that observed spiders doing it, and slowly pulled the leg away, measuring how much the silk thread bent before it let go, to get an idea of how strongly it adhered to the leg under different circumstances, and to test the effect of these 3 anti-stick features. The first feature is found on the tarsi, the last segment of a spider's legs. Each tarsus is covered in setae, which is what we call the hair-like stuff on spiders. And these particular setae on these particular leg segments point toward the end of the leg and have little barbs or spurs on their outer surface. These spurs catch the thread before it gets to the actual surface of the tarsus, which prevents the little balls of glue from actually making contact with much surface area. Also, as the leg was withdrawn from the silk, the glue droplets sort of slid down the setae, and by the time they were at the end, they were only in contact with the thin tips, so there was very little surface contact. Thus, very little adhesion, and the droplet would just let go. Also, all of the droplets in contact with setae don't reach the ends of those setae simultaneously. All of the pulling force is really just applied to one at a time, then the next, then the next. So there's really no cumulative adhesive effect. While they had some dismembered legs lying around, they scraped the setae off a few of them and stuck them onto the sticky strand, and sure enough, the strength of adhesion was about 7 times greater than when the setae were present. So these little setae make a huge difference. The second feature these spiders have that prevents them from getting stuck in their own web is a behavioral adaptation. When the legs are placed onto a sticky strand, they sort of go straight in, straight out, parallel to the tarsus of the leg itself, and thus all of those setae. This makes the letting go process really easy. The silk strand gets caught in the spurs of the setae, but is easily released because the spider pulls the leg out the right way. Not like this, but like this. The third feature had long been theorized but never thoroughly tested. As early as 1912, it had been suggested that maybe orb-weaving spiders coat their legs in some sort of anti-adhesive oil from glands associated with their mouthparts. So Briseno and Eberhard washed a few of these dismembered legs in hexane and some others in water and did the same test. In this case, it took about twice as much force to pull the leg off the sticky strand as it did when the legs were unwashed. So there does seem to be some kind of non-stick coating on these spiders' legs, and particularly on the tarsi, the only part of the leg that ever really comes in contact with the silk. They found that sticky silk adhered twice as strongly to the metatarsi, the next segment up the leg, and that didn't really change when they washed the leg. So whatever it is, it appears the spider applies it only where it's needed. And that, as best as we know, is how orb-weaving spiders don't get stuck in their own webs. So, with all of this engineering these spiders are doing, we start to get the impression that they're pretty smart little creatures. And we wouldn't be the first to think so. Back in 1962, S.M. Bays in New York investigated whether it was possible to train these spiders to react to different tones on a tuning fork. Over the course of 3 months, Bays put a bunch of these spiders through a little song and dance. He would put a dead fly that had been coated in quinine, the stuff that makes tonic water bitter, into the web, and vibrate it using a tuning fork that played the note C. Rudely, he did not sprinkle those flies with a dash of gin. A few minutes later, he would present a dead fly that had been coated in glucose, and vibrate that with a tuning fork that played C1, an octave higher. After 15 trials of this routine, all the spiders just started wrapping up the quinine fly, but biting the glucose fly. He then switched to different variations on the combination and order, but eventually went back to the first sequence. And this time, it only took 5 trials for the spiders to go back to the pattern they'd originally learned. They had retained that pattern, like they had an actual memory of it. Finally, he tried the same routine with glass beads that had no taste at all, and the spiders would discard the bead that was presented with the C fork, but they actually tried to bite the bead presented with the C1 fork. They had learned to associate the different tastes with the tones, and were actually trainable in this way. So we can see that these creatures aren't mindless automatons, they show behavioral plasticity, actually learning and adapting and remembering, at least to some degree. As always, all of the trapping and hunting and eating and growing is a means to an end. Reproducing. How do these spiders go about this? What does the whole life cycle look like? It begins with the spiders reaching maturity so that they can mate in the first place. And this seems to happen at different rates, with males maturing significantly faster than females, which mostly prevents spiders from the same egg sac, which are siblings, from mating with each other. And once the males mature, something interesting happens with them. They stop building webs. They actually lose the ability to make orb webs after their final molt to maturity. The aggregate glands of the spinnerets, which are the ones responsible for making the sticky capture spiral, no longer function. They've been known to eat the silk of the webs of females they're courting, or to feed on prey caught in the webs of other smaller species of spider, but without the web, food is hard to come by. In any case, at this point they go out looking for females, and they've only got so long to do that, since they only live for a few weeks after their final molt to maturity. This is where pheromones come in. A 2021 study led by Andreas Fischer found that the males were definitely attracted to the scent of specifically adult females, far more than the scent of subadult females. So the males are finding the females in their webs by scent primarily. Interestingly, Fisher's team also found that adult female Cross Orbweavers deliberately avoided the scent of other adult females. We're not quite sure how this works, but it probably has something to do with the females having their own little space where they're not competing with other females for mates. So what happens when the males and females meet? Well, as is the case with many spiders, this endeavor is fraught with danger for the male. Sort of. He doesn't have much to lose at this point, he can't catch food anymore, and if you can't eat, are you really living? But she just might kill and eat him at any point before, during, or after the actual mating event. Anyway, I was lucky enough to have been watching with camera in hand when this spider couple began their short but passionate relationship. The first job for the male is to identify himself and say, "I am not food, please don't eat me." He does this by making what's called a mating thread, a thread of his own that runs from the structure the web is built on to the edge of the web itself. Then he moves along this thread, plucking it, alerting the female to his presence. And she seems to pluck back, or shake a little bit. He's always got a second drag line behind him in case she lunges and he needs to abort the mission. But even if she does, he tries again, and again, and again. Eventually, she might decide she's up for it, and hang like this from her rear 2 pairs of legs, bunching up her front 2, and then the magic happens. This is what it looks like when they're actually mating. Then he springs away, not for fear of commitment like the males of some species after this event, but for fear of being eaten. When I first saw this, I thought for sure he was dead, but no, he survived this encounter. Now this has been studied in the lab, and it seems the male has about a 50-50 chance of surviving the whole courtship and mating encounter. And various factors determine that, but it gets complicated. And if you've been watching my Spider Basics series, I will be doing an episode there on spider courtship and reproduction, where I'll get into the details. It'll be a while, I've got a lot planned in between, but it will get here eventually. Eating dad actually is really beneficial for mom and babies, though. It turns out the male is a way better source of exactly the nutrients that the female needs to make lots of eggs than regular insect prey is. And when I say lots of eggs, an egg sac can contain 300 to 800 of them. It's a lot of baby spiders. And when they hatch in the spring, they stay together in a clump like this. If you blow on it, they all sort of go crazy for a minute before coming back together again. It's kind of fun to watch. But after a while, they each go their own way, to start their own webs. This they do by ballooning, letting out a strand of silk into the air, which actually interacts with electric fields to lift the spider off the ground, where it is then carried away by air currents. Spiders have been found thousands of feet in the air doing this, and they can cover tens or hundreds of kilometers doing it. They have no control over where they come down, though. They just have to take their chances. But enough of them survive to make their own orb webs, catch prey, and start the cycle again. And they know how to do this pretty much right out of the gate. Even these very tiny spiderlings already know how to weave orb webs. They'll grow through the summer, overwinter as juveniles, then mate and make egg sacs the following fall, with the females usually dying shortly after. They don't live to see the eggs hatch, sadly. So if you cried at the end of Charlotte's Web, and if you didn't, you're a monster, that part really happens. You would think that any creature that can produce 800 babies at a time would have no trouble keeping its species going. But in recent years, some surprising and concerning trends have popped up. In 2020, Martin Niffler and Dries Bonta published a paper documenting population densities of Araneus diadematus in Switzerland. They looked at some studies that have been done back in the 20th century, mostly in the 70s, but spanning from the 30s all the way to the 90s, measuring the population densities of the species in Switzerland and other places in Europe. And they actually went out and took population density measurements again in 2019, using more or less the same methods, walking certain paths in different kinds of habitat and carefully counting the number of spiders they could find. The average density of this species in Europe, according to the 20th century studies, was 0.067 spiders per square meter. So if you had a 1,000 square meter area, an area a little smaller than an Olympic swimming pool, you could expect to find about 67 of these spiders in it. And that average mostly held true in Switzerland as well. The 2019 numbers, however, were so low that the average number of spiders in that same area had dropped from 67 to less than 1. It was effectively 0. And in 2/3 of the sites surveyed, it actually was 0. No Araneus diadematus webs were found. This should concern us, as spiders are incredibly important ecologically. If you want to know more about why, check out episode 2 of my Spider Basics series where I look at the role they play in our environment. Niffler's study came on the heels of a landmark paper in 2017 that provided evidence that insect numbers in Germany had dropped by 75% in 30 years. Other studies since, from various parts of the world, including North America, have indicated that we're seeing massive declines in both insect diversity and biomass, the total weight of the insects in a given area. This seems to be indicating a massive bottom-up trophic cascade, an event where a change at the lower end of the food web has effects extending several levels above it. And it's likely that the Cross Orbweaver is a good indicator species regarding the abundance of insects, specifically flying insects, as that's primarily what they eat. The species still seems to be very common in North America, mostly around human settlements, so it's sort of hard to say what's going on. And the whole idea of insect decline is still a bit fuzzy because the studies all had their limitations and there are multiple explanations for the data that haven't been fully explored, but something dramatic is happening to invertebrates, and we should probably be paying attention to it. Cybugs did a fantastic deep dive video on this. I'll link it below. You should go watch it. It does seem clear the decline is happening in Western Europe at least. It's even been noticed as a significant decline in the number of insects killed on car windshields in recent years. Someone counted that. In any case, while this spider was once extremely common throughout Europe and even called the European garden spider in many places because of that, it's suddenly not so common there anymore. And while conducting the 2019 surveys, Niffler noticed that the webs of what spiders he could find seemed more fragile than those in previous years, which we know from lab experiments can result when spiders are malnourished. Now, research on this is ongoing, and you can actually get involved. The SpiderSpotter project allows you to make observations of spiders right from your phone and submit them, which is sort of like iNaturalist except just for spiders. But it's also got tools that let you submit particular data about them as part of the Spin City project, which is gathering data on the effect of urbanization on spiders. I'll link to their webpage in the description. You can go check that out if you want to contribute to our understanding of how the changing world might be affecting these animals. So this spider held some surprises for me, which sort of didn't surprise me, if that makes sense. I'd been looking forward to researching this species for a while because I knew I'd learned some amazing things, and I hope you have too. I was really blown away by the use of their web as a hyperacute auditory sensor. But that's what I've got for you on Araneus diadematus, the Cross Orbweaver. I think these are beautiful spiders, and I hope I've been able to share that appreciation for them with you. If you liked this video or found it helpful, click like, subscribe, leave me a comment. The engagement really helps the video to get around. And if you'd like to support this channel, check out my Patreon page, where you'll find extra material, research notes, random spider encounters I have, behind-the-scenes stuff. And Patreon is the very best way to support this channel. It helps out enormously. And I am so grateful to every one of my patrons. Thank you guys. Also, you can check out my Shopify store and get yourself one of these. Very popular with educators and NASA engineers. Probably. There's other merch there too. And that helps the channel out as well. Until then, keep an eye out for these magnificent spiders, give them some room and let them help us out, and take a moment to watch them work one day. You won't regret it. Thank you so much for watching. I hope you've learned something about this spider in your yard, and I hope to see you next time. Cheers!